Hello, guys. You probably have heard about the Black-Scholes formula of European option pricing. This model was published by Black-Scholes and Merton in 1973 and has remained widely used in the financial industry to this day. So in this video, I would like to tell you about the main results of the model and how these results can be derived. First of all, the model tells us that a European call option of time to expiry tau and a strike price K is given by this formula. Here, ST stands for the price of the underlying asset at time t. Phi is a cumulative distribution function of the standard normal distribution. D1, D2 are two convenience variables defined by these two equations. R is a risk-free interest rate, and K is a strike price. Moreover, the model tells us that the European call option price satisfies this partial differential equation with a boundary condition given by the option price at the time of expiry. So this formula says if at the time of expiry, the asset price is higher than the strike price, then the option price is equal to the difference between the asset price and the strike price. If, however, the asset price is lower than the strike price at the time of expiry, then the call option price has no value. Its price is zero. So next, I'm going to show you how these results can be derived. But first of all, let's talk about the assumption of the Black-Scholes model. So the model assumes that the asset price is given by this partial differential equation, which is called the geometric Brownian motion. It consists of two terms. The first term is called the drift term, while the second term is called the diffusion term. The parameter of the drift term is called the drift coefficient, while the parameter sigma of the diffusion term is called the volatility. Here, Wt is a standard Brownian motion. That means its increments are independent of each other, and each increment follows normal distribution, and the variance of this normal distribution is given by the length of the time increment. So we next need to look at what a European call option entails. So a European call option of expiry date T and a strike price K allows its holder to buy the underlying asset on the date T at strike price K. And similarly, a put option allows its holder to sell 1 unit of the asset at price K on the expiry date T. So this allows us to figure out the price of the call option immediately at the time of expiry. So as explained earlier, the call option price is equal to the difference between the asset price and the strike price if the asset price is higher than the strike price. Similarly, the put option price is equal to the difference between the strike price and the asset price if the strike price is higher than the asset price. If these conditions are not satisfied, then the options have price zero. Then the question is to figure out the price of these options when the time is before the expiry date. So first of all, let's derive the Black-Scholes equation. So suppose the call option price is given by this function f, which depends on the asset price and time t. Then imagine that we buy 1 unit of the call option and we also short x units of the asset. So at any time before the expiry, our portfolio has this value. We have bought 1 unit of the call option, and hence we have the CT here. At the same time, we have shorted X units of the asset, and therefore we have to subtract the total value of the assets. Now we would like to apply Ito's lemma to VT, the portfolio value at time t. So that gives us this stochastic differential equation. And my moving the terms around after expanding the differential of the asset price, we get this expression. If we take a close look here, then we will notice that if we choose the number of shares to short to be equal to the derivative of the call option price with respect to the asset price, then this SDE will have no more diffusion term. That is, the coefficient of the WT will be 0. In other words, the increment of the portfolio value becomes deterministic. There will be no more risk involved in this investment. However, if we think about it, the risk-free rate of return on this market must be unique, because otherwise one can always short a lower return asset and long higher return asset, and thereby taking a profit without taking any risk. Based on this reasoning, we can equate this term to R times VT. So that gives us this equation here. Here are the risk-free rate. So that means in the very small time interval of dt, the value of our portfolio should have increased by R times VT. And that is again given by this expression. So by moving the terms around, we will obtain the Black-Scholes equation. All right, so next, let's look at the Black-Scholes formula about the option price. So the motivation here is the PDE that we have derived is not so straightforward to solve because we see it is a non-linear equation. So we'd like to take a different approach, namely to consider the option price in the risk-neutral measure. In this measure, the asset price, that is a geometric Brownian motion, can be expressed in a slightly different form. We see that we have replaced the diffusion coefficient with a risk-free rate R, and we have replaced the Brownian motion is a real-world probability measure with a Brownian motion is a risk-neutral measure. So we can solve this SDE is a risk-neutral measure in exactly the same way as we can solve the SDE is a real-world measure, and then we will arrive at this expression. Then by risk-neutral pricing methodology, we know that the call option price must be equal to the expected value of the discounted payoff at the time of the expiry. And of course, we need to take this conditional expectation with respect to the information that's available up to the time of pricing, which is denoted as T here. So next, we can evaluate that conditional expectation. To do that, we can separate the two terms in that conditional expectation, and we have this expression here. We see that both terms involve the condition of ST being greater than K, and we would like to express this condition in terms of the Brownian motion. That's straightforward. So this condition can be immediately transformed into this inequality, and that means WT, W prime at T minus T must be greater than this expression. Now we know that W prime of T minus, capital T minus T has the normal distribution with variance capital T minus T. So we can rewrite W prime T minus T in this form using a standard normal distribution, using a variable of standard normal distribution. This way, we can express this inequality in terms of this random variable z. And for convenience, we define the variable d2 as this expression. Then next, we can evaluate the conditional expectation straightforwardly. So it translates to this integral. Here we have the expression of the asset value, the asset price at the time of expiry. And here we have the probability density function of the standard normal distribution. Then we can combine these two exponential functions to arrive at this expression. And also we have taken out the constant terms. Then by rearranging terms in the exponential, we can rewrite this part as a probability of z being greater than minus d2 minus sigma times the square root of t, capital T minus t. And we can express this probability in terms of the cumulative distribution function of the standard normal distribution. And that is this expression. And on the other hand, the probability involved in the conditional expectation, well, we already know it. So that is phi of d2. So by putting together the two pieces, we arrive at the expression of the call option price. And that is exactly the same formula that we showed at the beginning. All right, so that's it for today. Thank you very much for watching. And I hope to see you again next time. Bye.